Thanks, Andrew. Okay, so reading from last week, there were originally I was going to assign three papers. Then I decided the Versal paper is really good paper, and we will do a questionnaire on it. But it probably is better to do it in a week or two since it has lots of different things in it, and I think will be more understandable after we cover a bit more. So reading from last week was one paper we'll go over today on directional single driver wires, and there was an optional one on Xilinx UltraScale Plus, and we'll talk about pieces of that paper today if we get far enough too. Okay, so for next week, two papers that I will recommend that you read: the Stratix 10 highly pipelined FPGA and routing architecture, logic and routing architecture. So this is a pretty major change in FPGA architecture where basically registers went into the routing wires. Still controversial. It's basically architectures are evolving in that area quite a bit still. So an interesting paper. Another paper that is about adding a more structured interconnect to FPGAs, so embedding what's called a hardened network on chip. And this paper gives an overview of why would you do that and how might you do it. And because I basically thought I'd have you read Versal last week, I still am not assigning it for this week, but if you want to go ahead and read it in 2 weeks, you'll be writing a summary on it. So this is Xilinx's latest FPGA architecture, lots of new features, including an embedded network on chip. So it actually adopted a bunch of the ideas from the middle paper listed here, and a bunch of other new features. So pretty interesting paper. Not going to put a questionnaire up for it yet, but if you go and read that, you'll be ahead of the game because there will be a questionnaire. All right. So I guess reminder that assignment 3 is due on Friday, and I'm working on getting assignment 4, which isn't as open-ended, won't be as hard, released soon. So hopefully that's released before assignment 3 is due or right around that same time. So watch for that. Before I go into the lecture, any questions on the assignment or anything? Give you a chance to ask if you've got any questions. Okay, so I take that as everybody finds, well, either you're nothing's confusing or you're shy. So hopefully it's nothing is confusing. Okay, so we were talking about routing architecture last week, and there are lots of different aspects to it. So there's more things to discuss. We talked about different wire lengths, different switch topologies. The next thing is electrically, how do we build these actual routing switches? Because there are quite a few different ways we could build them. So these are a few of the classic ways, the most common ways that you would build routing switches in a standard CMOS process. If you go to more exotic processes, there are other ways to build them. And in the last lecture in the course, we should look at a couple of those. But in standard processing technology, these are the main ways. So we can build a pass transistor controlled by an SRAM, just as I'm showing over here on the left. There are a couple different ways we can build tri-state buffers. We could build a couple of inverters in series to build a pretty powerful buffer. So that's usually how you build a powerful buffer, is you build a little inverter driving a big inverter. Okay, so that's what that buffer represents typically. And then to make it tri-statable so that it can either drive a wire or let some other switch drive it, we can put a pass transistor on its output controlled by an SRAM cell, and we can do that for a bunch of different routing wires. So this would be a certain routing wire, R1 here, and it would allow us to connect programmably to a few different routing wires, say R2, 3, and 4 through these different pass transistors. Okay, so let me erase that. That's not the only way you can build a tri-state buffer. The fact that you have a buffer which has a finite drive strength driving through a pass transistor, which also has a finite drive strength or a non-zero resistance, it basically slows things down a bit. So there are other ways you can build tri-state buffers. You can basically have the strongest inverter you could build, which means you have one pull up and one pull down. So you've only got one transistor between ground in your output or power in your output. It's basically the best you can do in terms of getting the most drive strength or the lowest resistance for a certain amount of transistor size. But in order to turn this into a tri-state buffer, we need to have an SRAM cell to say whether or not it's enabled, and we need these gates to basically make sure that if this SRAM cell has a 0, no matter what the input is, that we turn off both of these transistors, and the output wire is left alone for some other switch to drive if it wishes. Okay, so that's an alternative way you can build a tri-state buffer. Has an advantage of basically getting good drive strength out of the final transistors, because we only got one transistor between power and ground, but the disadvantage of some extra circuitry here in these gates that's actually in your signal path, so it's between input and output, so it adds some delay, and obviously it adds some area too. But that's an alternative way to build a tri-state buffer. And then we can build something that is in the FPGA world called a direct drive switch. So it basically is almost the opposite of this tri-state buffer switch, where we have a buffer and then a bunch of pass gates. We instead have a bunch of pass gates controlled by SRAM cells. So this forms a MUX. That is another way of building a MUX. And that goes into a buffer. So again, that buffer usually is going to be built out of a small inverter followed by a big inverter. The reason you do that is the small inverter has small transistors, therefore it presents a small input capacitance. It drives a larger inverter, which has bigger transistors, which means this output wire, which is large, has a high capacitance, that's an entire routing wire going between blocks. It can be more quickly charged or discharged by this final inverter. Okay, so that's called a direct drive switch. And a key thing to notice is it's not tri-statable. Okay, that is a regular buffer, which means it can't be turned off. That's different than this tri-state buffer up here or over here, which can be turned off. They can be electrically disconnected from their output and leave something else to drive it. Okay, so those are a bunch of different ways we could build things. That leads us to, we're going to try breakout rooms again. So that leads us to our first, let's see if I can manage this properly. So let me bring up my Zoom here. And there it is. Okay, so I'm going to attempt to do breakout rooms. While I'm doing that, I'm just going to give you a couple minutes to discuss in small groups the strengths and weaknesses of each of these types of switches. Okay, so they all have trade-offs in terms of how much area do they take, what kind of delay do you get, and when you're thinking about their delay, remember that these output wires in each case are large and therefore highly capacitive. And do they create any differences in terms of routing flexibility? Or what you can do with them? Do they put any constraints on you? So think about that while I attempt to remember how to create breakout rooms, because I have so many windows and computers that I forget which one is controlling what. So let's see here. Okay, let's see which of these is controlling the meeting. Okay, I think the other one is controlling the meeting. So I figured out how to create breakout rooms. So I'm going to put people into 5 breakout rooms. We'll just go for a couple minutes. Just brainstorm. Well, maybe a couple minutes is too short. We'll go for a few minutes. Just brainstorm with the people in the breakout room on these questions. Okay. Welcome back, everybody. Let's see. So I guess my first question: how did the breakout work again? So this is the second time we tried it. Was that? Did you? Hopefully, I was in one discussion. Did you have useful discussions, or did you have 5 minutes of awkward silence? Feel free to just type into the chat or speak up. Okay, looks like at least a couple of questions came up. We got one good and a question. Questions are good. So okay, so I see some goods. That's good. Yeah, 5 minutes of awkward silence is probably not more. You probably have enough of that in the pandemic already. So I'm glad to hear there wasn't too much of that. It seems like. Uh,
Yeah, we needed to have the circuit diagrams for the discussions somehow.
oh, that's interesting. So the circuit diagrams don't show up because once we're
Yeah,
in the
we
breakout
we, we
room, we
lost
lose
that.
that. Oh, that's interesting. Okay.
And I even tried to share my screen, but it was disabled. So
Oh, that's annoying. Okay, I guess if it happens again, the slides are on Quarkus, so you can quickly go to Quarkus and open them. Everybody can go and look at them. I don't know if there's another way I can do that. I don't think I can send a screenshot through the chat, so I'll mess around with it tonight and see. Okay, so it seems like the feedback is mostly good, so that's good. Let's see. So questions people had. So question came up about the definition for routing flexibility. Yeah, it was vague. I guess I was trying not to lead you too much. And so let me walk through kind of my thoughts on this. So, well, we'll basically ask you guys. So anybody who wants to just jump in and say, what do you think of the pass transistor? What do you like about it? What do you not like about it? Let's just go through one at a time, and I'll throw in my thoughts. So, okay, so I see some good questions, but I'm going to start here with the pass transistor. So, what do you guys like about the pass transistor? What do you dislike about it?
It's fast if it's not in series.
Yeah. So the fact that it's only got basically in the signal path. So this is my input wire. Sorry, excuse the messy routing, and this is my output wire. Okay, so this is the kind of the key path. These are both big. So in my signal path, I've just got one transistor, and this output wire is going to have high capacitance. I can make this transistor pretty big in a certain area budget. So I can either say my pass transistor is small, or equivalently, I can say I can make a pretty big transistor with a given area budget. Big transistors have higher drive strength, which means they have lower resistance. My delay of any circuit is proportional to R times C. Okay? If you go and solve the differential equation of just a resistive capacitive circuit, so let's do a simple resistive capacitive circuit, which is an approximation of a transistor. A transistor behaves like a nonlinear resistance, so we can just ignore the nonlinear part, pretend it's just a constant resistance. It's not perfectly correct, but it's actually a reasonable approximation. So we get an R, and that R, this routing wire has got a lot of capacitance. We got a big C here, okay? And we're trying to look at what is the time constant. If we connect this to, say, VDD, how long does it take us to charge up this capacitor? And the solution of the differential equation is voltage is equal to e to the negative t over RC, which means our time constant is RC. All right, so to get to after R times C seconds, we will have made it 67% of the way to our final value. Again, this is an approximation because transistors are not really linear, but it is a key result that our delay is proportional to RC. Okay, so we can make a bigger pass transistor with a given area budget. It's going to have a lower R. That's going to be fast. Except, and now let me bring up, let's see if I can bring up OneNote to draw this. Okay, so Kate, I just told you why pass transistors are good for if I just had to connect one pass transistor to run one routing wire. But you said it's not good if I have a whole bunch of routing wires connected together. Is that right?
Is that what? Is that the only reason they're not good?
That's actually the key reason. and let's just look at why that is. So you're exactly right. And let me draw out. So I just drew out that RC circuit. We can generalize. I don't think I've done this yet. Remind me if I've basically drawn you a picture of the Elmore delay. Have I done that in this class before? Andrew, you tend to have a good memory. Do you recall that or not?
No.
Okay. So I just drew out that if I had a simple, sorry, let me change this. Okay, if I had a simple pass transistor that is trying to charge or discharge, doesn't really matter, a routing wire, that routing wire is basically a big capacitance. Okay, so that's what I've got. I can approximate that circuit by a resistance, and that resistance is smaller if the transistor is big, discharging a capacitor. Okay, and if I solve the differential equation of what happens if I try to charge it up, or what happens if I try to ground it and discharge it again, I get that that solution of, V is proportional to e to the negative t over RC, which means my switching time is proportional to RC. All right. Now let's take a more complicated case. Let's say I have a case where I have a buffer. Okay, so let me draw that. So I've got an inverter that is going to drive a pass transistor. Okay, so I've got an SRAM cell. I put a 1 in it. I'm driving a big routing wire. But that's not the end of my route. I need to go through another pass transistor to get to another routing wire. And I've got several of these in series. Let's say I've got 4 of them. 1, 2, 3. Let's say I've got 4 of them in series. Okay. And that's my final routing wire. And at the hanging off that routing wire is a little inverter that goes into, let's drop all the inverter. Let's just say it goes into a mux. Doesn't really matter. But we're going to go into a multiplexer and into our logic block. Okay. So I want to know the delay from basically, this is the output of some other logic block. I want to know the delay from here to this point where I'm about to go into the other logic block. Okay, so I want to go from 1 to 2. Okay, so if I really want to get that delay, I actually have to fire up a nonlinear circuit simulator like SPICE. And I have to tell it, here's my transistor characteristics, here's my wire capacitance, here is how big all my transistors are, and it'll give me the answer. But that doesn't give us a whole lot of insight. And we can get an approximate answer by basically approximating the circuit. Okay, so what do I do to approximate this circuit? Lots of ways to do it, but one that it's not extremely accurate, but it gives you the right big picture. So it's good for building intuition, is to, again, linearize the whole circuit. So what do I mean by linearize the whole circuit? It means I replace this driver by an equivalent resistance, and we'll call that R drive. Then I replace this pass gate by an equivalent resistance, R pass. Okay, and these are going to be a function of how big the transistors are that I use in these. And then I've got a capacitance here. So that's the capacitance of the wire plus all the switches hanging off of it. The wire is the biggest piece, but all the switches can be lumped into that too. Okay, that was one pass transistor. Now I got to go and I've got another one here. Okay, so we do this whole thing again. Put another R pass, and that's we got another R wire, and then we've got another R pass, and then we've got another capacitance of the wire. And I did 4 of these, so I get one more R pass, and I get one more capacitance. Okay, and then off of this, it'll go into our mux. This is our 0.2. Okay, and this is our 0.1. Okay, so I just turned this into a linear circuit. And you might go, okay, well, what am I going to do with that? Now I'm just going to put that in SPICE, so I didn't save anything. Well, we can extract the main time constant of this circuit. For the simple circuit that I drew up here, I told you the time constant is RC. This circuit is a bit more complicated. It's not quite clear, well, what R, what C, what would be the time constant of this? There's something called the Elmore delay. Okay, the Elmore delay comes from, again, writing out the differential equation for this system. And the solution is more complicated. But basically, the dominant response, the dominant exponential, again, has a time constant. And to get that time constant from the dominant response, what we do is there's a very mechanical procedure that's pretty simple to follow. We take every capacitance in here and we look for each capacitance. Let's start with this one. We look at how much resistance there is between it and the drive point. And we say we're gonna have to discharge that capacitance through that resistance. So that's going to give us some R times some C. And we add that up. So it's the sum. Whoops, let me change that. So it's the sum over all the capacitances. Yeah, I think that's probably the best notation I can think of. Basically the resistance to ground of that capacitance. Yeah, so let's say we're going over all the capacitances I, and there's a certain resistance for each capacitance to ground or the driving point, and we multiply by that capacitance. So we just take every capacitor and we figure out how much resistance is there between it and the driving point. Or you could say it and ground if you consider the driving point to be ground. Okay, so let's say we do that for this system. What you would find is the Elmore delay of this is R drive plus R pass. Okay. And let me highlight what I just did. I just took these resistances. Those are the resistances that all the charge on this first capacitor has to flow through. Let me change my color here. Okay, so all the charge on that capacitor has to flow through those resistances. So we take R drive plus R pass and multiply it by C. And all my capacitances in this circuit are the same because all my routing wires are the same. Okay, then I repeat that for the next one. So let's just change my color. So this next capacitance, I go, okay, that capacitance. Well, let's check in the chat. What is the resistance that the charge on that capacitor has to flow through to make it back to the driving point? So just type it in the chat if you know, or shout it out. I want to see if anybody's following me here. So I'm looking at this particular capacitor now. I'm on to the second one. Right, so it's R drive plus 2R pass. It's this. Okay, so I can just write that down. So it's R drive plus 2R pass times C. Okay, I can keep doing this. So for this next one, let me change my color again. So I look at this capacitor and I say, okay, how much resistance do I have to go through? I have to go through all that blue resistance that I just circled. Okay, so I wind up with R drive plus 3R pass times C. And the last capacitor is R drive plus 4R pass. Okay, and I multiply that by C. Okay, so what you notice is essentially I'm getting resistance building up. I've got this, you notice that these R pass terms keep getting bigger, right? There's 4R pass here, 3, 2, 1. So as I keep adding more routing segments in series, the resistance that they have to be discharged through keeps going up. So if I add all this up for this particular example, the Elmore delay would have been the resistance of the driver times 4C plus 1, 3, 6, 10. 10 R pass times C. So our pass transistor resistance is becoming a problem. It's getting multiplied by a big constant. And if I add one more wire in series, I'm going to get another 5 R pass times C. So actually my delay, if you work through what's happening, my delay is going to grow quadratically as I increase the number of pass transistors in series. So I double the number of pass transistors in series, my delay is going to go up by a factor of 4 for large numbers of pass transistors in series. So it means that long distance routes are going to be a big problem with this. If you have all pass transistors, they're going to get super slow. Does that make sense to everybody? Okay, so pause there. Seems like that made sense. No one is jumping up and down saying it didn't make sense. This Elmore delay is very useful. Okay, so the technique that I just showed you of linearize your transistors and then compute the Elmore delay is very useful for getting intuition about delay in digital circuits. It's not going to give you the exact answer down to the picoseconds, but it will be pretty good at telling you which circuit is faster than what circuits are faster than which one is faster. It also gives you intuition and basically where you might want to spend some area to make certain transistors bigger. If you look at, well, what would do the Elmore delay? You can see which transistors essentially are going to have the biggest impact. And that can be easier to see with a simpler linear model like that rather than running lots of spice. Okay, so hopefully you understand what's good and bad about pass transistors now. Let's move on to tri-state buffer switches. And I see so basically tri-state buffer switches, we don't get this kind of quadratic growth and delay. Their delay is very simple. If I went and did that Elmore delay exercise, you're going to see that every single routing wire that I connect just has the same delay. It's linear. If you go through 10 switches and 10 routing wires, and then you compare that to going through 20, well, the delay of the 20 is just twice as big. So it's very boring. It's very predictable. It's much better if you have a lot of routing switches in series. So you need some of these. So that sounds good, but basically they have the weakness of they take more area. If you add up, you look at either of these, this one or this one, they've got more circuitry than our pass transistor did. So for a certain drive strength, they're going to take more area. But because you can connect them in series better for long distance routes, they're going to be better. So that hopefully is clear. Okay, the direct drive switch. So the direct drive switch is kind of the opposite of a tri-state buffer. And I see there's a question from Camilo of, how do you do this with no tri-state, right? I've got a routing wire here, and you're saying I cannot disconnect this buffer from it. And that's exactly right. With a direct drive switch, you cannot disconnect this driver from this routing wire, which produces a major limitation on your switch pattern. You can only have one of these direct drive switches driving a certain routing wire because you cannot turn it off, okay? You can have multiple input wires that you can select from. So these are all different inputs. But they all have to be kind of close by so they could all make it into this switch structure. And anything that maybe is a long routing wire, maybe there's something on the other end of the routing wire where you think maybe this could also drive it. Maybe that could have an programmable switch. Well, with direct drive, it can't. Okay, because only one without being able to tri-state the buffers, only one switch could possibly drive any one routing wire. So it's a major limitation on your switch pattern. And I guess there was the question of what do I mean by flexibility? Yeah, that's effectively what I mean by flexibility here. The direct drive switch has a major limitation on flexibility. Exactly one of these direct drive switches can drive any wire. Okay, so you can connect as many wires as you want to inputs, right? You can make, instead of 3 pass transistors here, I can make 6 or 8. So I can have lots of inputs and they have to all be kind of close together so that I can connect them all to one structure. But in terms of how many switches can output onto a certain wire, it's exactly one. Does that make sense? I'll pause there for a second. If it doesn't make sense, put a question in. And if it does, be the person who moves the class forward by saying, yes, it makes sense. All right, so I've got at least one person who says that. Yeah, Camille's asking a good question. Can we use a combination? Maybe direct drive for long distance, tri-state for shorter ones? And yeah, you can use combinations of these. So I could use some pass transistor switches if I wanted to, some tri-states, some direct drive. I could mix these in all sorts of different ways. And actually a good question is, well, what would be logical ways to combine those? And we'll see some of that as we go through the lecture. So it's something you can think about of what are ways that are likely to be productive to combine them. Okay, let's move on. So the next few slides actually I've already talked about, so we'll flip through them pretty quickly. So pass transistors are small, but as I showed you with the Elmore delay, you get quadratic growth and delay when you hook a bunch of them in series. I didn't show this, but you can again use the Elmore delay to show that they're also really bad for fan out. Because if I go back to that Elmore delay diagram I had, if I started hanging lots of different routing wires off of here, so I hung another one off with a certain R pass and a certain C, sorry, this is getting kind of messy. All of these capacitances kind of get multiplied by this R drive. Okay, so it's difficult to make a driver big enough to keep the R drive times all this capacitance small. So high fan out's also a problem. It's not quite as big a problem as connecting them in series. So yeah, so that's the problem with pass transistors. So we really can't. Early FPGAs, actually for many years, FPGAs did just use pass transistors. But as the chips got big enough that you might have to connect a whole bunch of switches in series to cross the chip, they became problematic. So nowadays you can't really build a large FPGA using all pass transistors. Your worst case delayed across the chip is just way too big. Okay, you can use them though. You could have some, and just make sure that your routing algorithm understands that it is not a good idea to connect a whole bunch of them in series. Okay, so tri-state buffers. As I said, there are a few different ways you could build this. So this is a tri-state buffer where we built a couple of inverters, and then we've just got one pass transistor on the output. In FPGA routing, it's pretty tempting once you build a couple of inverters that you might want to go from a certain routing wire to several routing wires. So you might build several different pass transistors all connected to the same inverter chain. And that's what I showed you on the previous slide. And we also saw this, where we have kind of a traditional way you build a tri-state buffer. So we already talked about this, but basically they're bigger and slower for a single switch, but they have linear delay when you connect them in series. So they're much better for routes that go through a whole bunch of wires connected together. So we can build architectures that are all tri-state buffers. It's all right. They're a bit bigger, but they will work. And the paper that you were assigned last week showed that, at least in 0.35 micron, which is definitely an older technology, that having 20 to 50% of your routing switches tri-state buffers like this, and the rest pass transistors, was a good choice. Basically, the router would use the pass transistors when it didn't need to connect a lot of wires in series, and would use the tri-state buffers when it had to. And the combination achieved a better result than either one of the switch types could by itself. Okay, so the direct drive switch essentially flips this structure. Let's see if I can move this video out of the way. Okay, so the direct drive switch basically flips this structure. We take these pass transistors from the output, and we instead put them on the input. And we do the switching before the buffer. Okay, so why might that be a good idea? At first glance, it seems like, well, why do I want to do that? Like, why would it possibly be better just to invert these things? Like, invert the order of them. So you have to think a bit about electrically what's happening. Think about what capacitances there are in this circuit. And remember that wherever you have a big capacitance, you need a big transistor that has low R, or it's going to be really slow. So what do you think? What have I achieved by flipping it this way? I'll give you a hint. So if I look at this output side, this is a big routing wire. Okay, it goes past multiple logic blocks. That's long, that's high capacitance. How much capacitance do I have here? Yeah, so it's pretty low. So if I basically keep these pass transistors, very close to this buffer, which I can do, I can just say, well, I'm gonna lay it out that way. I'm gonna keep these pass transistors close to this buffer. Then these wires are quite short, and their capacitance is small. So that means that I can make these pass transistors pretty small, and that means that they have high resistance, but that's okay, because if my delay is proportional to RC and C is small, then it's still all right, even if my R is big because I use small transistors. So this flipping of where I put these pass transistors allows me to use smaller pass transistors and get a good speed. So I can either take that as a speed win, or I can take it as an area win, or I could take it as both. Okay, I see Camila, you have a question, but what about the wire before the pass transistors? So yeah, this one is big. Okay, so this is another routing wire. So these routing wires are also high capacitance. But that's okay. If I repeat this structure, what's driving that wire is another one of these direct drive switches. Okay, so it's another structure with, pass transistor here, uh, and a direct drive buffer. Okay, so this buffer needs to be pretty big. It needs to be powerful to drive this large routing wire. And remember, this buffer is just another copy of this buffer, right? This is like a kind of repeated structure. This pass transistor is not discharging this capacitance, okay? So that's not what is discharging. It is discharging this capacitance, right? That is my path. The charge will flow from this capacitance through this pass transistor into the buffer and to ground. Okay, that's my signal path. So when I calculate the delay of, this is getting kind of messy, but if I calculate the delay of this part of my circuit, it's R pass times this C small. Okay, so that's pretty good. Okay, so we've got a light load, so we can use smaller pass gates. And then we make the buffer non-tristatable. Okay, so what does that do? We already talked about that. It has this major limitation of we get only one drive point per wire, so our switch pattern now becomes very constrained. But a non-tristatable buffer is smaller and faster than a tri-state buffer. So you just go back here and look at them. You look at a non-tristatable buffer, its output is just an inverter like that. And a tri-statable buffer has to have extra gates in it, or it has to have extra pass transistors in it. So it's bigger, and for a certain area budget, it's not as it doesn't have as lower resistance, and therefore it slows things down. Okay, so removing the tri-state on this will make a switch that's smaller and faster than a regular tri-state buffer. Okay, for long connections, we still have a buffer in the signal path. So when we connect a whole bunch in series, the repeated structure that we have would always have a buffer driving every single wire. So again, we get linear increase in delay. We don't get the quadratic increase in delay that we got for pass transistors. Does that all make sense? Okay, so I'm going to take that as nobody seems too confused. Let's see, would it make the approaches to combine the approaches with a tri-state buffer after the routing transistors? That is a great question. Okay, so let me erase this. So you're basically saying, okay, I like this technique of let's do our switching right before the buffer where we have low capacitance. But you're saying, why not make this a tri-state buffer? And we could do that, right? We can make that a tri-state buffer by essentially, using this structure. So it costs us some area, but it gets us flexibility, or essentially by putting some more pass transistors on the output, which will have to be big ones. But I can put these pass transistors on the output to different routing wires, and that's another way of making this tri-statable. And yeah, you can combine them. So you don't have to make this a regular buffer. You could make it tri-statable. When people use the term direct drive, that's basically just been defined to mean not tri-statable. But there's another case you could do where you make it tri-statable. So that's a good question. And that's actually a great lead into one of the assigned readings, because they actually look at both those cases. Okay, so this is work by Guy Lemieux, who these days is at UBC. And what he looked at is directional versus bidirectional routing. So, which is related to direct drive, but not exactly the same thing. So the first thing he notes is that when you build a what are basically conventional routing patterns, the routing patterns that were dominant in FPGAs at the time he did this work. You would either build pass transistors, which allow you to connect, always allow you to connect from one wire to the other. Okay, so pass transistors have this nice property that they're bidirectional. So this could be my input, and this could be my output. Or same pass transistor could actually do it the opposite way, right? That might be my input wire, and that might be my output wire. I could use it either way. Um, when architects started mixing tri-state buffers into their routing architectures, they kept them bidirectional. What I mean by that is they would put two tri-state buffers at the end of a routing wire. That's what I'm showing here. So there are two tri-state buffers. You could turn the red one on, or you could turn the green one on. And so it allows you to go either way through this routing switch. So my signal might come from the left, and let's see if I can get a better highlighter. Okay, so my signal might come in from the left and go out this way. Or I could have configured this by instead turning on this switch to actually send a signal the opposite direction. So by basically having back-to-back tri-state buffers everywhere where I had a switch point, my architecture is bidirectional. Signals can flow either way between routing wires. And down here, this just shows, same pattern, but you're going the other way. Okay, so I wanted to go from left to right. I just turn a different tri-state buffer on. But what Lemieux notes is that this guarantees that you're going to leave half your tri-state buffers unused, because it makes no sense. It's electrically not even legal to turn both these tri-state buffers on at the same time, right? That would form some kind of latching structure, which is obviously not what you want. So it's guaranteed that you will never ever turn on more than half your tri-state buffers. So he asked, well, is that the right thing to do? So this is basically a little channel with 4 routing wires, and he's drawing out, if we have this bidirectional switch pattern, so Fs equals 3 in this case, so every routing wire, when it ends, can connect to 3 other routing wires. And he has a traditional kind of bidirectional switch pattern here that is implemented with multiplexers. So multiplexers basically are going to be that structure of pass transistors then driving a buffer, okay? In this case, a tri-state buffer. So he's using something that's almost a direct drive switch, but he's still able to tri-state the output. And he's drawing here, what is all the circuitry I need for every kind of group of 4 wires in this Fs equals 3 switch block. And he needs 4 muxes, and each mux has 3 inputs, and he needs all of these tri-state buffers. If he instead takes pairs of wires, and he basically decides that one of those pairs is going left and the other one is going right, and he only builds the switches that you would need to support that usage. So he's pre-decided which direction each wire will go if it is used. Then he gets this pattern down here. Okay, and I'm not going to walk through the details of the pattern, except you can see it's removed a lot of switching. Okay, so he's removed basically half of the area. Now it is a less flexible switch pattern. He's predetermined that certain wires, if you want to keep going, like certain wires can only go right, certain wires can only go left. He's created pairs of them basically with this constraint. But in so doing, he's able to remove a whole bunch of switches. Okay, so we can't say this is a good idea or not without running CAD experiments. So clearly for a certain number of wires, it saved a bunch of area, but maybe it makes it super hard to route circuits, which means it's a really bad idea. Before we go on to those CAD experiments, he then also looked at another question. With traditional bidirectional routing, okay, so we've got these back-to-back tri-state buffers at every switch point where a routing wire ends. We have multiple spots that can drive a wire. So if I look at this wire here, let's see if I can find one that's a good candidate. Yeah, maybe I can. Basically, I need to make I don't know what's going to drive this particular routing wire. There are multiple drive points for it. Okay, so there's a driver here from the left, and it's not shown, but somewhere out here there'll be another driver from the right. And the logic block also might connect to it. So we have to make sure that all of those multiple drive points for the wire, all the things that could drive it, can be shut off. So if the logic block wants to drive this particular routing wire, we would turn on, let's see if I can get a different color. We would turn on this pass gate. Whoops. We would turn on this pass gate, and we have to make sure that we can turn off that tri-state buffer and that one. Okay, and they're tri-statable, we can do that. If instead, let's say we turn on that tri-state buffer, we need to make sure that we turn off, the output from the logic block. And we can do that with this pass gate. But basically, with bidirectional wiring, we have essentially multi-driver wiring, multiple things that can drive a certain routing wire. We have to make sure we can shut them all off, so that we never have two things trying to drive the same routing wire, because they're just going to fight each other, and the circuit's not going to work. Okay. So the next thing that Lemieux points out is that when you have these directional wiring, so now he's again decided that each wire can either go left or right, but it's pre-decided. There's only, for example, this wire, there's only a driver from the left. There's no driver from the right. And that's fine. We can still leave, we can still leave a tri-state on its on the routing switch that is going to be able to drive this, and we still have a tri-state, or the ability to turn off the connection from the logic block output. So it's fine, it all works. But these pass gates, again, have to be pretty big, because these routing wires have a high capacitance. So all these pass gates coming out of this logic block have to be pretty big. So the last thing that he looks at, which is the move to full direct drive, is, well, if we didn't have this logic block, come out and connect to these wires with big pass gates, but it instead fed into the direct drive muxes, then we no longer need a tri-state, because we only have one spot that can drive the wire. We don't have to turn it off. Okay, but it is a significant connectivity constraint, because let's say this wire is a long wire, spans maybe 4 logic blocks. Only the logic block that is near its left side, its left end, is near this mux, and therefore could actually drive it. All the other logic blocks, it's not really an option, because you'd have to drag some wire a really long distance to get into this mux, and that doesn't really make sense. That's going to take way too much area and be way too slow. So we have this significant constraint on connectivity, that only one thing can drive it, including, if we go all the way to direct drive, which logic blocks can drive a routing wire. So does that make sense? Or are there any questions? Maybe I should ask these questions the other way. Okay, it looks like none. Okay, so how well does this work? And this is where you have to get into, well, what can a CAD tool do with it? Like, from an electrical perspective, this looks great, right? I've gotten rid of a bunch of big pass transistors, and instead I can use little pass transistors in these muxes. I've gotten rid of tri-state buffers, and instead I'm using simpler non-tri-statable buffers. From an area versus drive strength point of view, this is all good. It's going to be faster. It's going to take less area. But I put all sorts of constraints on what my routing algorithm can do and what my switch patterns can look like. So they do experiments with VPR using a CAD flow. So they augmented VPR to understand these kind of switch patterns. And they did use the CAD flow very similar to what we looked at last week to investigate across a bunch of benchmark circuits. So this bar graph shows the area for every benchmark. The most important number is basically the average. Okay, so what's the geometric average across all of the benchmarks? And they've got 2 different points here. So they've got, let's just change the switch pattern. where we get rid of the back-to-back tri-states that allow us to go in either direction, and instead we're going to decide each wire is either left going or right going, or in the vertical direction, up going or down going. So we pre-decide that. We only build the switches that allow that, but we don't really change. We don't take the tri-states off of the buffers. So when they do that, they get an area reduction. So it works pretty well, and it's actually a very big area reduction. That's about almost 20% area reduction, which is large. If they take the tri-states off, okay, and that produces more connectivity restrictions. Now you can only have logic blocks that are near the drive point, the end that is the drive point of a wire. Those are the only ones that could actually drive that wire. So it's a big connectivity restriction, but we made our electrical design simpler, smaller. It's a net win. Okay, so the area goes down even more. So we've got an area win of almost 25%, which is a huge area win. Okay, what happens with delay? When they make the architecture, again, the most interesting numbers are this geometric average. When they make the architecture directional, meaning they rip a whole bunch of switches out of it in order to, and say, every wire's got to be left or this one has to be right, it does cost them some speed. All right, so that restriction on the connectivity, the removal of some of those routing switches, leads to more circuitous routes in some cases. So they lose a little bit of speed, but not very much. Maybe 2 or 3%. But when they actually go further and they say, let's get rid of the tri-state buffers, make them all non-tri-statable, they gain so much electrically. Like the buffers and the routing switches themselves get faster, given the same area budget, that it more than compensates. Okay, and again, this actually added some more connectivity restrictions. Only logic blocks near the drive point could actually drive it, but that connectivity restriction still was not so bad as to outweigh the electrical advantages. So it's a big win again. This is not quite a 10% speed win, but close to it. Okay, so often we want to combine area and delay because the area delay product is the opposite of, or the inverse of throughput. Again, the geo mean is the most interesting number here. So what happened overall? Two lines again. What if they basically just change the switch pattern to make it directional? It's a net win. They've got actually a big win, nearly 20% area delay improvement. But if they go further and they basically make an architecture that's all direct drive. So every wire has a direction. It has one driving point. You can't tri-state any buffers. They've got more than a 30% improvement in area delay, which is huge. So that's a great improvement. So their conclusion is go all the way, right? Go all the way to a directional architecture, all direct drive. Okay. Any questions on the paper? All pretty clear? Okay, so if so, I'm going to basically quickly talk about at the same time. Basically, there was some industrial work going on. So this is the Stratix routing and logic architecture. And it basically reaches similar conclusions. So that's the punchline. So one of the questions that the paper published on the Stratix architecture by Altera is how it proposed using these direct drive switches, which no previous Altera chips used. And one of the questions that they asked and also answered with their internal version of VPR is how many direct drive switches should we have? Because you could do it for some of the wires, but not all. So basically, Michael's question, is there an analysis of a mixed architecture? So this is essentially that mixed architecture. So what I'm showing here is the speed on average across a suite of benchmark circuits, or delay, so smaller is better. And on the left side is what fraction of the switches are direct drive. Okay, so they look like, what fraction are direct drive? So on this side, they're all direct drive. Okay, so 1 means 100% of my switches are direct drive. Small pass transistors that form a mux and they go into a non-tristatable buffer. On the left side is basically an architecture that doesn't use any direct drive. It instead uses basically buffers driving big pass transistors. So that's one of the ways you can make a tri-state buffer. And pass gates. So it uses a mix. Some pass gates on certain routing wires have pass gates. Certain routing wires have tri-state buffers. And they vary the fraction. Okay, so right in the middle, you'd have half direct drive and half non-direct drive, where the non-direct drive are also a mix. So the result actually was pretty surprising. So I was at Altera when we did this, and interestingly, for delay, it was best to just do all direct drive. There are two curves here. One is a mix. The kind of magenta one is a mix of length 4 wires and length 8 wires. So there are two different wire lengths. The blue one is what if you have a mix of length 4 and length 16 wires. They both show roughly the same trend, that direct drive, having some direct drive is really good for speed. So you see there's a gain in speed as you start adding direct drive in both cases. And it's never a bad idea to just keep adding direct drive for speed. So the gains start to flatten out because basically the CAD tools are smart enough that they start moving the critical path onto these faster direct drive routing wires. And that's why you get a big gain at first. And then as you make more and more of the routing architecture direct drive, you get less speed gains because the CAD tools have basically already found the parts of the design that need to use the fastest wires and have put them on the direct drive. So that's why you see this kind of slowdown in the improvement. Okay, so what happens for routing channel width? This is a pretty surprising result. Basically, okay, so on the y-axis is how wide do we have to make the routing channel. Again, using that CAD flow that we discussed a week ago, find the minimum channel width for each benchmark, add 20%, average that across all the benchmarks. That's how you figure out the channel width. So, and again, the x-axis is what fraction of the routing is using direct drive. And there are two lines, one where the routing architecture has some length 4 and some length 8 wires. That's this line. And one where it has some length 4 and some longer length 16 wires. Okay, so what does this say? It's actually, again, quite a surprising result. It basically says if your wires are not too long, so this purple line, that it doesn't actually affect your channel width very much at all to go to all direct drive, because this side is all direct drive. This side is, on the left, is no direct drive. So that's kind of surprising. It means that these restrictions of, some wires must go left, some wires must go right. A logic block can only drive the wires that start near it. The CAD tools are actually able to handle those restrictions, and they really don't need a significant number of extra tracks. Now, when we go to this architecture, which is a mix of length 4 wires and longer length 16, now we do see some increase in channel width. Right? As we go to all direct drive, there is an increase, but it's moderate. It's under 10% increase in channel width. So let me ask a question, see if who's following along. Why do you think the blue curve, which has this longer wire mix, shows a somewhat different trend than the magenta curve, which has a somewhat shorter wire length? Any ideas? Why does direct drive have an impact on channel width when we had a mix of length 4 and length 16 wires, but it didn't really have an impact on channel width when the wires were shorter? So let's see, so more shorter length wires get used for directional routing. So I guess at the 100% direct drive case, everything's directional. Okay, so we've made every single wire in the architecture directional, can't be tri-stated, etc. So I guess at the 100% case, everybody, long or short, has had their switch pattern change that way. And yeah, so Edmund's saying that the restriction on only accepting local drivers, and I think that is exactly the reason. So as wires get longer, okay, so you go to length 4 wire, when you go to direct drive, let's say this is a wire where we put the switch on the left side, okay? only logic blocks near the left side can get into that mux and drive it. Okay, so that's a restriction for a length 4 wire of maybe only 2 or 4 logic blocks right around here, right around its drive point can get onto it. But it's not too bad because the wire's not that long. When you go to a much longer wire like this, length 16 wire, we still, let's say that's a wire that's going to the right, we can still only get onto it from logic blocks that are right near its start. Okay, well, let's make this simpler. Let's say it's only 2 logic blocks right by its start. This routing wire has lots of switches hanging off of it. It's going into lots of other routing muxes. So basically, it's a relatively expensive resource to waste. As you make routing wires longer and longer, there are more and more switches hanging off of them. You kind of don't like to waste it. And the restriction that you can only get on it at one spot becomes more severe. There's just a higher probability that nobody around this zone near its start wants to use that wire. There may be something out here that would love to use it, but in a direct drive architecture, they can't. And that restriction is a bigger deal for longer wires than for shorter wires. Because for shorter wires, the fraction of blocks that are close to the start point of the wire versus the blocks that are somewhere along it is essentially higher. So when you start adding really long wires in, direct drive for them is a little more tricky. That's where we started getting some increase in channel width. But overall, it's still a very good result for direct drive. The CAD tools are very, very able, surprisingly able to tolerate this restriction. Okay, so that was channel width. The channel width's not the whole story, right? So we really care about area. And because direct drive switches are smaller, right? They're very electrically efficient. Even though out here we have, for at least this blue curve, a higher channel width when we're using all direct drive switches, the actual routing area has still gone down. So this is showing the routing area per tile, per logic block, basically. And it just keeps going down for both these architectures. Basically for both wire length architectures evaluated, the routing area just kept going down the more direct drive you put in. Okay, so direct drive, in summary, it imposes significant limits on the switch pattern. You can't drive a wire in the middle. You can only drive it at one end. And your routing is directional. A wire goes from one end to the other end. They could go either way. But surprisingly, that only modestly increases channel width. And because you've electrically made your architecture a lot better, you actually removed a bunch of switches. You've gotten rid of some big pass transistors and replaced them with small pass transistors and muxes. You've gotten rid of tri-state ability. You get a net area benefit and delay benefit. So the Lemieux paper quantified this as 9% improvement in delay and a 32% improvement in area delay. And the Altera paper also found a significant benefit. So because of that, Altera went to 100% direct drive switches in their Stratix chip, which is 130 nanometer, and Xilinx did the same thing a couple of years later in Vertex 2 Pro. So direct drive came to dominate. I think we'll break there for now. One place I can give up. The one place where in recent years direct drive isn't always used is these really long wires. Okay, so when you get really long, expensive wires, that's the place where mixing in some traditional tri-state buffers is useful. So for several generations, Xilinx and Altera went to 100% direct drive. In their most recent chips, they've brought back some tri-state buffers for the longest wires because those really long wires are basically very expensive. And they're getting even more expensive because they're built high in the metal stack using thick metal that has lower resistance, and you can only build so many of those because there just aren't that many really fat metal layers, and because the wires are big, you can't fit as many wires. So there's an increased cost to wasting those long wires, and because of that, in the most recent chips, those wires have switched back to tri-state buffers so that they can be driven at multiple points and there's less risk of wasting them. But the bulk of the routing is still done with direct drive. So it's kind of the workhorse switch now. Any questions on any of that? Okay, so there are no questions. How about we take a 5-minute break to 5:30 and then we'll go on to the next topic. And I'll be here in case you have any questions that you were too shy to ask. Okay, so we're back. And I want to talk about long wires some more. So this is a picture from a food process generations ago, so it's only gotten more extreme since then. This is a picture from Stratix, which was 130 nanometers. And what I want to show here is just basically what the metal stack looks like. So the transistors are down here at the bottom. Okay, so they're really small. And they drive contacts, which are tungsten, to get up to the first level of metal, which is here. And then you can go up to through copper vias to higher levels of metal. So here's the second level of metal. And this particular metal layer is running essentially in and out of the screen. You can also go up to the next metal layer here, which is running left, right. Okay, so the directions alternate. And you notice that as you go higher and higher in the metal stack, basically the wires get taller. And you can see that they also get wider and spaced further apart. And as I said, this is actually getting more extreme with every process generation. So you get more metal layers, and the top ones look, basically the bottom ones are getting more and more dense to connect all these increasingly tiny transistors. The top ones are really not getting much more dense in order to keep the wires relatively tall, relatively wide, and therefore relatively low resistance if you go into significant distance. Okay, so if I want to go a long distance, I actually want to use wires that are relatively high up in the metal stack because they have lower resistance, which means they can go a longer distance in a certain delay. These wires down here low in the metal stack are okay if you're not going very far. They're pretty resistive, but if their length is not very big, your resistance is proportional to your length, you're still okay. But if your length gets big, then the resistance becomes high and they become very slow. So in the typical design, you do have some connections that span a significant distance. You wind up with some things that go, cross the chip or at least cross a fairly large module. So, they're not spanning 4 logic blocks or 8 logic blocks. They might be spanning a much bigger distance, 32 or 64 or 100 logic blocks. So you want to be able to make those connections quickly. It's not the majority of your connections, but if you don't have any way to connect those up quickly, they're going to limit the speed of your circuit. So long wires are a challenge because of the fact that you have to put them high in the metal stack for them to make electrical sense, and you can't have that many wires high in the metal stack because they're wide and spaced out a lot. Okay, I actually already talked about this just before the break, that for direct drive, the fact that you can only have one drive point for a wire is more limiting when the wires get long. So we want to make sure that we don't waste our long wires. And one of the ways I talked about is the most recent chips tend to use tri-state buffers for long wires rather than direct drive. That helps you drive at multiple points and makes it less likely you'll waste those expensive wires. But that's not the only thing that you do. So another problem you have is that if I'm up on one of these, if I'm on some long wire, say a wire that spans 24 logic blocks, to get down to a certain transistor, which is how I get into the routing muxes, I got to go down through this whole metal stack. So I get a whole bunch of vias and little bits of metal hanging off of me. And if I do that at every single logic block I pass, I'm going to do that many times. And that's actually going to slow down my long wire. Okay, so it's costly to get down from the top level of metal all the way to the transistors. So we've got these expensive wires that we can't build too many of, and they're actually kind of hard to get on and off of because we got to go up and down the metal stack. So what FPGA architectures have evolved to is to have a form of routing hierarchy. So long wires connect only to shorter wires instead of directly to the blocks. So let me show you what that means. So this was a technique that was brought in by Stratix and has been used by lots of chips since then. So the idea is Stratix's kind of most common workhorse wire is a length 4 wire. So it spans 4 logic blocks. And the logic blocks can have programmable switches that allow them to drive straight out of a logic block onto one of these length 4 wires. Actually, sorry, let me not draw that one. Drive straight out of one of these logic blocks onto a length 4 wire, and then programmable switches let you get right back into a logic block. So that's kind of what we've looked at so far for island style FPGAs. But for long distance routing, they have some much longer wires. So they have length 24 wires horizontally and length 16 wires vertically. The lengths are different because in Altera architectures, usually the logic block's not square. Okay, so that seems kind of odd. Why would you have it longer in the horizontal direction than the vertical direction? Physically, they're not longer. It's because the logic block is actually laid out to not be square. So it turns out that 24 units horizontally is physically about the same distance as 16 units vertically. And so it's a reasonable choice for this. You can't drive onto these wires, these long wires, directly from a logic block. And you can't get off one of these wires and go directly into a logic block because, as I said, it's too hard to get up and down the metal stack. And there also aren't that many of these long wires. So we kind of want to be able to use them as sort of freeways to get where we want. So what Stratix does instead is a logic block, if it wants to get onto the long wire network, it has to go out onto the length 4 wires first. So that's what I'm showing here. The length 4 wires do connect into the programmable switches, the direct drive switches that drive these long wires. So from a length 4 wire, you can get onto one of these long wires. The long wires can connect to each other. So from this horizontal one, I can drive onto this vertical one. And the long wires can drive back onto some length 4 wires. And from those, you can get back in. So this basically forms a hierarchy. If I don't have to go too far, I can just use the length 4 wire network. And I can connect a bunch of length 4 wires together if I need to. If I need to go further, I use the length 4 wire network a little bit, for a wire or two. And then I get onto the long wire network. I can go as far as I want, maybe all the way across the chip. And then when I get near the end, I drop back down through some programmable switches onto the length 4 wires that can get me into the logic block. So this is basically a technique to get maximum utility out of these relatively expensive long wire routing resources by forcing you to go through a cheaper part of the routing hierarchy first. And that gives you more flexibility in how to get onto the long wire network. You can only connect every 4 spots. So these long wires can't connect to length 4 wires at every single spot along their length. It's only every 4th spot. So say here and so on. And they can drop down through the metal stack, through all those vias. They can connect to some programmable switches, then get onto a length 4 wire. But again, only once every 4 logic blocks do they have that whole stack of metal and the ability to go into some programmable switch to get onto a length 4 wire. That limits how often you have to do it, limits the loading on this length 24 wire. But those length 4 wires are pretty good at making local connections. If you can get within 4 units of the logic block you want to get to, well, then one length 4 wire will get you the rest of the way. So it's good enough because of the fact that you're not connecting directly to the logic blocks, but instead to these shorter wires. So Stratix has a mix of wire types. This is like relatively typical. As I said, the length 4 wires are the workhorse. That's what most of them are. For extra speed, it has some length 8 wires, and they behave a lot like the length 4s in terms of their switch connectivity. They can connect directly to the logic blocks and so on. And then they have a relatively small number. Only 12% of their wires are these length 16 and 24 long wires, and those are essentially a hierarchical network, as I just talked about. In Stratix, all these switches are direct drive. As you go to some of the most recent chips from Xilinx and Altera, as I said, basically the long wires have typically gone back to tri-state. Because this challenge, if you can't build that many long wires, has just only gotten worse. So one of the things architects are looking for is ways to make sure they can use all of that long wire, all of that top metal effectively for long wires. So any questions on it? If you have any, jump in or type them in chat. One interesting thing about Stratix is, so I was part of the team that designed Stratix, and it was a big break for Altera. Altera had always done a form of hierarchical FPGAs before that, and the last one they did was Apex 2. And Stratix was done in Toronto by a team that Altera had acquired, and it was done in the same process. So usually FPGA companies don't do two chips in the same process because it's too expensive. But in this case, they did because they had their traditional evolutionary path and they had a new one. So this actually lets us do a kind of rigorous comparison of an island-style FPGA to a particular hierarchical FPGA. And this is across the suite of benchmarks, Altera's internal benchmarks at that time. And basically for small, medium, and large designs, the island-style Stratix architecture was always better. This is basically how much faster is it? And it averaged 40% faster, but on the biggest designs, it was even more. So pretty strong validation that island style works well. And it, at the same time, it's not shown on this graph, but also Stratix took 30% less area. So it was about a 2x improvement in area delay, so twice as efficient. So I think it's pretty strong evidence that island style does work better than hierarchical. As I just mentioned here, island style FPGAs have adopted some hierarchical ideas. We talked earlier about how they use logic blocks with local interconnect. So that's one hierarchical idea. And I just talked about another one, which is the longest wires, which are really expensive, kind of reach them only from shorter wires, which gives you a form of hierarchy, but it's a more irregular hierarchy. So it's not that hierarchical concepts have gone away, they're still used, but FPGAs that are kind of strictly hierarchical in the way we talked about a few lectures ago are not as efficient for at least big FPGAs. Okay, so I'd like to highlight a few routing architecture principles because there are lots of different moving parts to a routing architecture, but there are a few things that are kind of useful guidelines. So first, moderate length wires are the best. So if you're going to guess one wire length, usually length 4 is pretty good. In the latest chips, the number of wire lengths is kind of increasing because you're getting more and more metal layers with different resistance characteristics. So you're getting routing architectures that still have mostly moderate length wires, length 4, maybe length 3 or 2, but a wider range of different lengths of wires. And also scrambled or irregular switch patterns work well. So we talked earlier about how the very regular patterns like the original Xilinx chips that use that what's called the planar architecture, where track 0 wires can only connect to other track 0 wires, were problematic. Another principle is that if you think about your routing paths, all routing paths start at the output of some block. They go through one wire or maybe a whole bunch of wires in series, and then they come into the logic block. So there's some muxing structure get into the logic block, and then usually some local routing, and then there's the input to the actual primitive, so a lookup table or a multiplier or a RAM. As you think about what the routing path consists of, you want to make sure that none of these steps going from, say block output to wires, you don't want any of these steps to be really hard, okay, where there's very little flexibility, because that's going to be the choke point that makes your CAD tools really have trouble. You also want to avoid making any of these steps really, really easy. So if you built an incredible number of switches between wires, then your CAD tool may never have any problems going from one wire to another wire, but it probably means you wasted area, because then all the CAD tool's problems are going to be going from the block outputs to the wires, or from the wires to the logic cluster inputs. So you kind of want to achieve balance. You don't want to have too many switches in any one of these sequence of switching decisions. You don't want to have too few. Okay, so what does that mean? So it means it's good to make the block to routing interface similar for all blocks. So we think about logic blocks. The typical way that they work nowadays is you have a logic cluster input, and from there you go to some kind of local routing, often a crossbar or a partial crossbar, and then you go to the primitives, like the lookup table inputs. Okay, so we look at a RAM block. Do we need this local crossbar at all? And that local crossbar, well, let's see. Maybe I'm giving too much answer on that. If you didn't see that quickly, let me ask if anybody has an opinion. So in RAM blocks, should I leave this local crossbar in or take it out? What do you think? If anyone can read really quickly, you already have a hint. So I put it in for the logic blocks because I noticed that, I often have signals that are shared between two lookup tables. And I also often have signals that come out of, say, one lookup table or one flip-flop and go back to another one. Okay, so there's some local connectivity, and that's why I put this local crossbar in. In RAMs, we're not actually going to see a data input, data 0 come into a RAM block, and we're not going to have a signal come in and go into both data 0 and data 5 and so on. That doesn't really exist in RAMs. We're also not going to typically see a RAM's output be fed back to its input. It's kind of weird. It's not very clear what that would mean. So some of the reasons that we put this local crossbar in the logic block don't appear to exist in a RAM. So should we just take it out then? So it's one of those ones where you got a 50-50 shot. So if you've been waiting for a chance, just if you type in yes or no, you got a 50-50 shot. If you type in maybe, you're for sure right. So, okay, so Marius, you were definitely right. Okay, I see people love my maybe idea. Okay, so I'm going to answer this one. So it's actually a good idea to leave it in, even though, as I said, the original motivation for putting it in, the ability to broadcast signals, they come into the logic block once, you broadcast them to a bunch of lookup tables, or you connect outputs of lookup tables to other inputs. That really doesn't exist in a RAM. In DSP blocks, sometimes it exists, but often it doesn't either. The reason you leave it in is that it actually makes the routing path more similar. Okay? When I'm going past a logic block, I basically, if I have a local crossbar, getting to any input of the logic block is okay, because my local routing will let me get to the right LUT. If you make your RAM blocks work the same way, where if you get to a certain input of the RAM block, you have the same ability of maybe your crossbars are such that you can get to any one of the inputs of the RAMs can get to any internal signal, or maybe you didn't build such big crossbars, maybe you can get to 15 of the internal signals. Basically making it look like a logic block makes your routing architecture more regular. No matter whether you're starting or ending in a RAM or a logic block, your CAD tools see a problem that's about the same difficulty. If you take the local routing out of the RAM block, then getting a route that ends in a RAM block is harder, right? You have to get to a certain specific input on that RAM block rather than just getting to a certain group. because you can count on the local routing making the final stage of connectivity. So for that reason, it's actually better to leave whatever local routing you had in your logic blocks in the other blocks too. You can, in a RAM block, let's see, let me draw the RAM again. So let's say I have a RAM block here. A RAM block typically is not going to have its outputs feed back to its inputs. So that part of the local routing you can remove. It just won't get used. But the part of the local routing that allows you to take some input and choose what signal on the RAM you connect it to is useful because it gives you the same difficulty of routing problem to get into the RAM block as you had for logic blocks. The other thing you want to balance is essentially what we looked at for PCI Express. We want to make sure that all of our blocks are similar in terms of how many inputs and outputs they send out to each piece of a channel, right? So we've got a piece of a channel here. We want our logic block and we want our RAM block, for example, to try to connect about the same number of signals to the channels that they're adjacent to. And this one, I think, hopefully you remember, it's because our channel width is, proportional to lambda, the number of used inputs going into that block, times r bar, the distance that they went, divided by 2. So if we're going to use the same channel width everywhere, we want to make sure that all the blocks connecting to our channels are trying to connect about the same number of signals. If we have a really big block, if our RAM block is really big, then we should probably make it span, a larger area so that we can have it connect to multiple channels and spread its inputs and outputs out. Does that make sense? It's the last comment, which might be a tricky one. Does this mean anything for partial reconfiguration? Let's see if I can move down here. So let me see if I can tell you what I mean by that. So in partial reconfiguration, which we talked about earlier in the course, we said, well, we might have some piece of a design that is here. Maybe we implemented module 1 in this part of the chip, and we implemented module 2 in this part of the chip. And maybe we're going to actually swap things in. We have module 1A, and at some point in time, we actually want to swap that out and put in module 1B. Okay? And we talked about that earlier in the course, that's tricky because we basically need to, when we put in module 1B, it has to use the exact same wires at this boundary to M2 that it talks to as M1A. All right? So does that have any implications for how hard it is to do partial reconfiguration? This might be a tricky question, but basically when I'm trying to make a connection from if I go back here, let's see. When I'm trying to make a connection, I usually go from the output of a block through a bunch of routing wires, through some local connectivity, and then finally to the input of a primitive. If in partial reconfiguration, I said I just have to route to a specific wire, which is kind of the obvious way to make partial reconfiguration work. I put in a new block of circuitry, M2B, so there's a certain LUT in here, and it can do anything it wants to other LUTs in M2B, but when it comes to talking to this other module, M2, that it's in a different partial reconfiguration region, it's got to use the exact same wire that M1A used. Every module I want to swap in there has to use the exact same wires to get in and out of the partially reconfigurable region. That's kind of the obvious way to make partial reconfiguration work. Now M2 is just listening to certain wires. Its lookup tables are listening to certain routing paths, and what's driving those wires has changed. It doesn't care. It's still getting the signals it needs. So from a logical perspective, it would all work fine. And this is actually how partial reconfiguration was originally done, is the CAD tools, if they wanted to partially reconfigure this region so both M1A and M1B could go in at different times, then both M1A and M1B had to use exactly the same wires when they left the region, The problem is that's actually a significantly harder routing problem because usually when you're trying to get to, say, a certain lookup table, you've got a couple of extra layers of muxing. You've got the muxing to go from routing wires into the logic block, and then you've got the muxing to go from the logic block, through the local interconnect to the LUT. Getting to a specific routing wire is actually harder because you just lost a couple of levels of muxing. So the CAD tools would really struggle with it. Routing completion is more difficult. So in the more recent versions of partial reconfiguration, uh, basically the CAD tools will automatically insert boundary LUTs that don't do anything. They just pass the signal through. Um, and what that does is now you've got a wasted LUT, but basically when the CAD tools are being run in this partial reconfiguration mode, they're still trying to route to a lookup table. They're not trying to route to a specific wire. And that lookup table is just constrained to be right on the boundary of the region you're trying to connect to. And it's no harder to get to that lookup table because you still have that muxing, which is the connection block to get into the logic block, and you still have the muxing that is the local interconnect. It's no harder to get to that lookup table than any other one. So it looks more like a normal routing problem. Okay, so hopefully that made sense. Okay, so you got to be careful not to make some of your routing problems harder than others. And the industry kind of missed this with partial reconfiguration for quite a while, where when you turned on partial reconfig, the routing problem got harder. It's been resolved in the later versions of the CAD tools by essentially sticking lookup tables in on the boundaries between partial reconfiguration regions. Okay, so to highlight a few of these principles, which of these architectures is better? So the one on the left or the one on the right? They're both using length 4 wires. They both have a channel with 4 wires in them. So is there any difference? Is one of these better than the other? Okay, so everybody likes left. So why is left better? Left is better. Why? So less regularity. Yeah, it is less regular. It's a one wire option. Every block sees the same wires. Yes, those answers are all correct. Symmetric for every block. So you're all right. So on the right hand side one, I'm just going to highlight that you can basically connect these two red blocks with one wire. So that's good. But if I want to connect these two blue blocks with one wire, I can't actually do it. I would have to actually use a switch to connect two of these length 4 wires together to make that connection. So it needs 2 wires and an extra programmable switch. But if I look at the other side, I have more options. Even though I don't have more wires, because their start points are all staggered, I have actually more options. I can make both the red and the blue connections with one wire. Okay, so a principle is that basically hard boundaries are bad. This routing architecture on the right has all the wires starting and stopping at the same spot. So it's created essentially a hard boundary. Like at this point, these two blocks are close together, but they can't use really fast routing paths because of the decision I made to just have all the wires stop there. So it's not a good idea to do that. It's better to stagger the start and end points, and you get more routing choices without more area. Okay. So basically what we've got on the right is more like what traditional hierarchical FPGAs did. And we already talked a bit about that we use hierarchy in uninstall FPGAs, so we won't talk about that anymore. Let's see. Okay, it looks like we have one contrarian. Let's see, let me read what Camilo said here. The right one would make it easier to connect them to longer wires than they all share a vertical via. Let me think about that. Okay, so you're saying because all of these could connect to a longer wire because maybe all their drive points are the same? Possibly. But in general, I do tend to like the left one better. So, okay, so let's talk about a few more of these principles in practice. So the cluster interconnect is the local routing inside of a logic block cluster. In the paper we read about that, it was fully connected. So you used fully connected crossbars, which is a lot. A crossbar, any pattern of inputs to outputs can be completed. So you can't block a crossbar. So it's very flexible. So that seems kind of excessive. I said it's not a good idea to have excessive flexibility in kind of any stage of your routing network because you're probably going to waste it. And there are studies that have shown that full crossbars are actually too much. You don't need them in your local interconnect within the clusters. Okay, and this is a paper by Lemieux and Lewis that looked at that. So this is their picture of a logic block. So it's got a bunch of lookup tables or BLEs and flip-flops. And in a full crossbar, let's see, what this is showing is basically some signals come in from the outside world. Okay, so we've got regular routing channels, and the dots represent programmable switches. So I can bring some signals in from outside of the logic cluster. And then once they come into the logic cluster, they're on some local interconnect. If this local interconnect was a full crossbar, then I'd have dots on every one of these crossing points. Basically, every input to a lookup table could come from any one of the inputs to the logic block. And similarly, the output of any lookup table could feed back to any of its inputs. And what Lemieux and Lewis looked at is that too much? Maybe that's more muxing than we really need. So let's start removing some of those dots and getting a more sparse switch pattern inside of the logic cluster. And let's see if that actually saves area. And they also want to leverage the fact that there's another stage of routing flexibility. So lookup tables, you can actually permute their inputs. So if you get to any input of a lookup table, you can always basically change the truth table to make it do the right thing. If you expect it to come in on input 1 and you instead come in on input 2 for a certain signal, just by changing the truth table, you can make it do the right function again. So lookup table inputs are what are called logically equivalent. If a router can get to any one of them, it's okay. So they leverage that fact as well. They don't actually need some signal from the outside world to come into this local interconnect and get to a specific input to the LUT. They told the router that it's okay to get to any input. So maybe the netlist said get to the first input. The router understood it could actually go to the last input instead, and it would be okay. They also made the switch pattern the same for every one of these basic logic elements. And the reason they did that is if all of these are the same, then when the router brings in connections and gets to some lookup table, it actually could guarantee that it could get to any one of the lookup tables because the switch pattern to all of them is the same. Okay, that actually allows them to tell the router that it's okay to swap where you start your signals. Signals coming out of the cluster can actually start, it can choose which one of these BLEs it starts the route at, because it can always do that. If it decides that it wants to use a different BLE than the netlist and placement had implied, it's okay. It can basically fix things up because if it could get to this BLE with a certain signal that needed to make it to it, it also can guarantee it can get to this other BLE that it might have swapped it to. So that means that the outputs are logically equivalent. So basically, they found a couple of extra degrees of flexibility. They don't have to get to a specific input on the LUT. They can just get to any input on the LUT, which acts like another stage of routing flexibility. And they don't have to start on their signals from the output of a specific LUT. They can start from any LUT because of the switch pattern they've chosen. They found that this was a good idea. They could remove a bunch of switches and save area. But for the best results, they should increase the number of inputs to the cluster. Um, so, see if anybody, why do you think that is? Why would it be a good idea? So they basically took a whole pile of switching out of here. Okay, they made all their muxes smaller. And then they found for best results, they should actually then add a few more signals coming in. Okay, so essentially add more inputs to the cluster and a few more switches out here to get at those. So why do you think that was a good idea? Might be a subtle question. It's maybe hard. So I'll give you a few seconds to see if anybody's got an idea, and then I'll tell you why that was a good idea. Okay, so nobody wants to take a shot at it, so I'll tell you. It's basically what I said about balance. So they've taken a bunch of switches out of the local interconnect, um, which was a good idea because the local interconnect was so flexible compared to the interconnect out here between the regular routing wire segments. But when they did that, now if they have 20 inputs to the cluster and that's what they physically build, and then they actually some of the logic blocks in a design try to use all 20 inputs, there's a high potential for failure, right? They're trying to get 20 signals through this local interconnect, and there only were 20 inputs, and they've removed a bunch of the switches. So the odds of getting through that, if you tried to use every single input, had dropped noticeably. But if they said, okay, we'll tell the CAD tools that you can only use 20 inputs, but we're actually going to build 24, then the hardest cases kind of go away. They'll never have to get, on only 20 inputs, get through this switch pattern. They can guarantee there are actually 24 inputs, and you just have to get, say, 20 through them because they tell the cluster never use more than 20, but then they actually build 24. Okay, so it makes sense. They basically compensated for their reduced intra-cluster routing flexibility. And now that they can get blockage, you don't want to try to use all of the inputs because that's equivalent to trying to use all your routing wires. Okay, so what they found is they can remove 50 to 60% of the switches in these crossbars. So that cuts their mux size by 2x or a bit more than 2x. Looking at the whole architecture, that was a 10 to 14% area reduction without increasing delay. It did make routing harder. Okay, so before their change, once the router got to the inputs of the logic cluster, it was basically done, right? The local interconnect was really simple. Once you got to any input, it was full crossbar. It was guaranteed it would get to any input to a LET that you wanted. Once they removed a bunch of switches, they couldn't do that anymore. The router had to actually search not just into the logic block, but actually had to go through the local routing and see if it could find a path to the LET it needs. So that made the router's job harder. So it did increase the router runtime significantly. They found between 2x and 7x. So the Stratix paper that I talked about earlier also used a similar technique. They took half of the switches out of the logic block local interconnect as well. So instead of using full crossbars, they used essentially 50% populated crossbars, had half the number of switches. So that can also have blockage. But they found that it was a good change. It gave them a 7% area reduction and a 1% delay hit. So it's mostly the same result as Lemieux and Lewis had. The big change is there's a little bit of a delay hit. And the main reason for that is the academic work, Lemieux and Lewis, assumed all the LET delays were equal. And in reality, they're not. So the lookup table is made out of a tree of pass gates. Inputs that go to the last part of that tree are faster. And most commercial CAD tools like Quartus take advantage of that. So we'll actually take the most critical inputs, the ones that are going to be speed limiting, and try to get them onto the fastest LUT inputs. And when you start removing switches, it gets harder to do that because the router's problem has become more difficult. Not every input to a logic block can connect to every input on a LUT. So it's less able to get the fast, the speed of input it would always want. It takes a little bit of a delay hit. This paper also said that it was possible to go below 50% switch populations. They could remove even more switches, but it got really hard to lay out. So they couldn't really get area gains from doing that, so it didn't. Okay, so I guess the point of all that was that it's an example of having excessive flexibility in one part of your architecture, these full crossbars, and you can gain by removing some of that excessive flexibility, taking a bunch of switches out in this case. When you do that, you often have to add some flexibility elsewhere. So Lemieux and Lewis said, well, now we have to add a few more inputs to the logic block, but the cost of doing that was less than the gains they got by removing lots of switches. Okay, so we just talked about how hard boundaries, lining all our routing wires up, are bad ideas. But in the island style FPGAs we've been looking at so far, it seems like we have a hard hierarchy boundary between clusters. Okay, so what do I mean by that? So these two red blocks can be connected with just one wire, and that's fast. If I move a bit closer, it doesn't really get any faster. Okay, so this blue block is right beside this red block, but it still has to use a length 4 wire. So it's not any faster. Now you can say, well, make some length 2 wires, and now it'll be a bit faster. And that's true. So maybe we could do that, make a few more wire types, and it helps. But there's basically a big jump in delay when we go from I'm in the same cluster, and I can use just the local routing, to I'm right next door, where I have to go out and use at least one regular routing wire. So can we do any better than that? Because physically, these two blocks are very close. Maybe there's something we could do electrically that gives us a faster path between them. This is a paper from Rupchen Singh and Rose, where they looked at that. So the traditional path that you'd have electrically coming out of a logic block is you go through some relatively large buffer. So this is probably, well, in this study, it was 2 inverters, a little inverter and then a big inverter. You go on from that output pin. In this case, they used kind of traditional tri-state buffer routing switches. So you get a pretty big buffer. You go through a pretty big transistor. You go onto a routing wire that goes between multiple logic blocks. So this was a length 4 routing wire. So it's pretty high capacitance. But you don't really want to go very far in this case. I want to just go to my next door neighbor. So from this routing wire, I go through a mux and into an input of this logic block. And this logic block might now have some local interconnect. So what they looked at is, well, this seems like a lot of circuitry to go to somebody who's right beside me. So they added in nearest neighbor connections. So that's this path here. So they said from the output of this lookup table in this logic block, we have just a buffer that drives a wire that goes straight into the connection block input mux of this logic block, and that should be faster. Okay, so they're basically looking at this path here, which got rid of a fair amount of circuitry and capacitance that you were traversing. And they did find that was a net gain. Okay, so that particular study found that they got 6% delay reduction by adding in these these nearest neighbor connections. It did cost them some area, okay, because they didn't remove anything. They just added in some extra inputs to this mux and an extra output from this block. So that did cost them some area. So it was a small gain, but it was a gain. And this is a pretty common thing that commercial FPGA architectures use as well. So in Altera chips, you typically have paths that are called nearest neighbor connections or sneak paths, where this logic block can basically drive signals out, bypassing the regular routing and just straight into the local interconnect of the logic block on its left and the logic block on its right. Okay, and similarly, it can take signals from the logic block on its left that go right into its local interconnect, and from the logic block on its right that go into its local interconnect. So it can talk, it's not quite as fast as being in the same logic cluster, but being immediately left or immediately right is not that much slower, because essentially there's some connectivity into each other's local interconnect. So it breaks down some of that hard boundary between logic blocks. Xilinx does something similar, but instead of going to just the left and the right, their chips typically go to 8 nearest neighbors. Okay, so everybody who's within 1 unit in the x direction and 1 unit in the y direction. So they have more nearest neighbors. So this looks kind of different. Any ideas? This might again be a hard question. Any ideas why Altera Altera/Intel and Xilinx chose different points? So Altera goes to 2 nearest neighbors, Xilinx goes to more, 8. So I'll give you a hint, because this might not be obvious, because I don't know if I've mentioned this before or not. Altera and Intel's FPGAs, well, the high-end FPGAs, the ones that are bigger, actually Gil has basically a good answer of different cost of using routing. It is because of a different cost. So actually both these are logical choices. I don't think there's really a right or a wrong. And they're driven by a fundamental difference in how these two companies make their chips. So for their high-end chips, so the Stratix series and Aria series, Altera and Intel have redundancy. Okay, so they can actually repair broken rows in the chip, and Xilinx doesn't. So that's kind of a fundamental difference. And usually you can't, in regular logic, you can't repair things. So SRAM arrays, if you build a big memory array, it's got lots of rows, as we saw earlier, and big memories are repairable. Okay, so normally they're built with, if you say there are 32 rows of memory, well, if you say there are 1,000 rows of memory, you actually build 1,001. And if one of them is broken, you basically program into some fuses, and you never use that broken row. Because you only advertise that you have 1,000 rows. So you can tolerate one being broken. Okay, so that is used all the time for SRAM, if it's a big SRAM. But for logic, it's much more difficult. So generally, for logic, you don't repair random logic. It's too hard to think about that. But FPGAs are pretty regular. So what Intel FPGAs do is they basically an entire row, which would have some logic blocks, some RAM blocks, some DSP blocks, etc. At the time the chip is tested, they test not only whether the whole chip works, but they test every single row to see if it all works. If there's a flaw in some row, that's actually programmed into some fuses on the chip, and basically every vertical wire in the chip, if it is advertised to the CAD tools and the end customers as a length 4 wire, it's not really length 4. It's really length 5. It spans 5 blocks. And it has enough switches that everything it can connect to in the 4th row, it can also connect to in the 5th row. What that means is that if a certain row is broken, when the device is programmed, you can actually skip that row. And because all the routing wires vertically are 1 unit longer than the CAD tools thought, it still all works. Everything can be shifted up 1 row without recompiling the design. So it puts some restrictions on the switch patterns. It means that the vertical wires are actually 1 unit longer than you think, so that you can always reach past the broken row. Xilinx doesn't do this because they just considered it too complicated and didn't believe that it would create too many restrictions on the chip. The reason Altera can do this is they actually started out with hierarchical FPGAs. And hierarchical FPGAs is easier to do this. They're more regular. I mentioned that I was part of the team that created Stratix. When we were acquired by Altera, it was just the head of engineering simply made it a requirement. Stratix will support redundancy, even though it's got a more complicated routing pattern. he actually had not made it a requirement, we wouldn't have done it because it was actually quite hard to do. And would have just said it's too hard. We're not doing it. It's too many limitations. But he just said that is not an option. You will do it, and it actually worked out in the end fine. There's some cost to it, but it's not excessive. So the two companies have very different approaches in terms of repairability. Altera says you will be repairable, and if that puts constraints on the architecture, that's okay. And Xilinx has decided it's too complicated and we will not use that kind of repairability. What that means is that vertical wiring is more expensive than Altera chips. So if this block could go to 8 nearest neighbors, so it could actually go to this one in an Altera chip, you'd actually need to go not just to this one, you'd actually need to also have a connection 2 rows above. Okay, so all the vertical wiring is always more expensive than an Altera chip because it's always 1 unit longer than you think. And that's a significant cost if the wire is really short. So you gave people the ability to go to just 1 block higher, but you really have to build twice as much. You got to make that wire two x as long. Xilinx doesn't have any such restriction. So having nearest neighbor interconnect to this block is no worse than having nearest neighbor interconnect to this block. But it is significantly worse for Altera, which is why they have chosen to do nearest neighbor interconnect only to things immediately to the left and right, because they're in the same row. So they use only horizontal routing. And horizontal routing isn't affected by this because it's all about being able to shift everything up to go past a broken row. So Gil is right. There's a different cost of using routing. For Xilinx, vertical and horizontal are basically the same cost. For Intel and Altera, vertical is always more expensive than horizontal because of the fact that you might have broken rows and your vertical routing has to be able to go past them. Okay, so that was a long digression. You can tell me in the course surveys whether that's interesting or not. So I've just got a few more miscellaneous routing ideas to point out. Any questions on any of that? How impactful is it to use the vertical connectivity? That's a good question. I don't think it's extremely impactful because of the fact that we have studies that we did at Altera that are similar to this that show nearest neighbor interconnect gives you a small improvement in delay, but it's not huge. The reason it's not huge is you're limited by your critical path, and except in an incredibly well optimized design that probably is extremely rare and may not exist, most of that critical path is not on nearest neighbor interconnect, right? It's going to use some longer distance routing, and that's why it's your critical path. But you can still get some gains by, if once or twice on the critical path, you can take connections and get them on this nearest neighbor interconnect, then it is faster. And it also gives you, for somebody who's really willing to micro optimize, maybe even go in and guide the tools, be really careful about how their design is structured. You can go to, if you really, really optimize, so you get more stuff on the nearest neighbor connectivity, you can go higher. So I guess it's a long way of saying I don't think it's a large impact, but it probably is some impact. Never quantified it. But I guess given this result that you get 6% delay reduction having nearest neighbor versus not having nearest neighbor, I think the cost of not having it in the vertical direction will be significantly less than that. So it's probably in the low percentages and maybe even less. The overall cost of making all your vertical wiring 1 unit longer is more than that. So it does cost a few percent of speed and a few percent of area to make all your vertical routing bigger, but it does improve yield a lot for big chips. And Andrew's asking, can't we lose the logic in the row but stitch vertical routes? So I think you're saying, okay, so you're saying I've got a broken row. So I was going to have a path that was routed like this. It's going to go out here, go up one, go there. And now this row is broken. Is that what you're saying? Actually, maybe I don't think I'm going to draw anything. So I think it's going to be too complicated to draw. So I think you're saying, could we rerun the CAD tools? Could you basically say, I had a path that was going to go maybe, I was going to use a length 4 wire to go from here to 1, 2, 3. I was going to go from this up to something that was 4 units away. Okay, so I use the whole length 4 wire. And now I've got a broken row. So this whole row is broken, it's programmed in fuses. So could I just, without changing my routing architecture at all, just basically say shift this guy up one. So now he's there, and reroute the connection. Basically say don't go out on that wire. Well, go out on that wire, but then connect to another wire and then go in there. Is that what you're saying?
Uh, so that's an interesting question. I was also trying to reason about the nearest neighbor connections. So let's say I have a nearest neighbor connection to the block that is right above one of the blocks.
Yeah.
And there's a dedicated nearest neighbor connection, but then the row in yellow is basically broken,
Right.
but I can only stitch it. Like I lose the logic in that row, but just stitch it to the row above.
So you could make nearest neighbor interconnect, but basically this is what you would normally build. You'd build a very short wire that goes from probably the top side of this logic block to the bottom side of this one and into the local interconnect. With redundancy, I have to account for the fact that that row might be broken. So I actually have to build a wire that's twice as long. Well, more than twice for probably the nearest neighbor. It has to go all the way to, it has to go through both blocks. Does that make sense? So that if this one is broken, yeah, I can actually reach the one above.
You already have a wire from the second to the third row, right?
Oh, I think you're trying to. Okay, so you're trying to basically say, can you connect those together? Yeah.
Yeah.
It's challenging. So I guess maybe this one is easier to see. Like, why does Altera make the wires extra long? Okay, so here's a length 4 architecture, and let's say I broke this. So the way Altera actually does it is this wire that they're using is really 5 long. Okay, so they can just go straight in. Let's say they didn't do that. Let's say they're still 4 long. You could say, well, maybe rerun the CAD tools. Well, that's what you'd have to do. You now have to rerun the CAD tools, telling it this row is broken. You've got to change all your routing to use different wires. And academics have sometimes proposed that, but it's impractical because the CAD tools take hours to run and don't always get the best answer. And where most of the money is in the FPGA market is actually people buying thousands of FPGAs or tens of thousands or hundreds of thousands and making systems with them. So they're just programming those. They're not running the CAD tools for every single chip. Because of the fact that it's just the wire is actually 5 units long, essentially the programming hardware just does a very mechanical change of the bit stream. It basically just shifts everything by one row and it all works out. Okay, it's actually a little more complicated now, but it can be done by the programming hardware. And if you do something where you have to rerun the CAD tools because you actually have to change which wires you use, it's just not practical because it would take hours, and for every chip you'd have to have an engineer checking that it was all okay and so on. I don't know if that fully answered your question or not, but it's an interesting one. So, I thought I'd answer that question anyway. I guess it's similar to, I think if you're talking about, I got another piece of wire, maybe I could stitch it by programming in the connection. Your timing models and everything have to assume the worst case. So this isn't just about area, it's also about timing. So if I have to assume this wire goes all the way up there, I always have to assume it's that long.
I see. Yeah.
Because the timing models have to take the worst case for any chip, which means they know all these wires must be 1 unit longer. They must timing analyze them 1 unit longer.
That makes sense. Yeah.
Cool. Okay. Last few miscellaneous routing ideas. So first one, speed unbalanced routing. So this is a general technique that you can use, I guess, in a lot of different ways. So this is a paper that I was a co-author of back in 1999 that showed one way to use this, but since then people have found other ways to use this property. Basically, only a minority of the circuit needs to be fast, just the critical paths. And on a suite of benchmarks, what I found is that you got about making 20% of the wiring faster. In this case, that was done electrically, just making 20% of the wires more spread out so their capacitance was lower. You got almost all the speed up that you would get by making all of the wires faster, because the CAD tools were smart enough to basically take the critical paths that were limiting your speed and put them on the fast wires. So this is basically across a bunch of benchmarks. What's the average speed if you have none of these faster wires? And this is what happens if you have all of your wires are faster. But you might not be able to lay that out. You might not have enough room to space all the wires out that much. If you only spaced out 20% of the wires, so they have reduced capacitance, you actually got almost all the reduction in delay you were going to get. Stratix 2, the paper on Stratix 2 that Altera published uses basically the same idea but in a different way. So this is a routing mux, okay? And this is a bit complicated to look at, but this is a 2-level mux. So a normal routing wire here goes through one pass transistor and then a second pass transistor and then into a pair of inverters. Okay, so that's this is a direct drive routing switch shown at the electrical level. But they take a few inputs. So here's a special routing wire, and it goes only through one pass transistor. So it goes straight into the second level of the mux. They're using a 2-level routing mux, but a few inputs are actually going straight into the second level of the routing mux. So they only go through one pass transistor. And they found that if they did this, they could get 4 to 5% more speed by making one fast input. If they try to make all the inputs fast, the area starts getting big because essentially they're making a 1-level mux instead of 2 levels. And as we looked at a few lectures ago, that actually takes more area because you need more SRAM cells. But just doing one fast input, they get most of the speed gain with only a fraction of the area cost. So it's the same idea. So do you think we can just combine this? So we can say, let's have a few fast inputs to the routing muxes. Let's also have a few fast wires where they're more spaced out and they're faster. It's one of those ones where everyone can have an opinion. So anyone want to take a guess at this? Do you think these will combine? Do you think they won't combine? What do you think will happen? Maybe getting towards the end, so maybe it's too much to ask for everything a yes. You start running out of gas if you do too much of this. So the idea is that so they partially combine, but if you start making too many special cases, like if 20% of the wires are extra fast, then 20% of the paths into the routing switches are extra fast, it can get hard for the CAD tools to line everything up. So as you do more and more of that, you have to be careful that there are still some options for the CAD tools to actually use all those speed ups at the same time, and they're not just conflicting. If they're all kind of independent choices, it'll be hard for the CAD tools to line them up. Okay, I think I'm going to not talk about this, and I think we'll leave it at that. So we'll talk about a couple more routing topics and then move on to clocking and other topics next week. So I think I'm going to leave it at that for today. Any questions? Okay, I think if there are no questions, we're done for tonight. I'll stay on the line for a few minutes in case somebody had a question but was shot.